Good morning, esteemed professors, and welcome to an exciting new experience with the Science Bus. I am Barbara Di Cicco, and in these video presentations, in collaboration with Wacebo, I will demonstrate the experiments that can be conducted utilizing the Science Bus kits. Today, in particular, we will discuss the static friction force along an inclined plane, and therefore we will have the opportunity to experimentally calculate the static friction coefficient. To carry out this experiment, which is well suited for high school BN students, we will make use of the mechanics kit. Let's proceed by meticulously screwing the rod into the base. We then take the clamp and insert the rod, which is equipped with the pulley, into its designated housing and securely screw it in place. In the other slot, we carefully insert the vertical rod and securely screw it in. Then we pass the string around the yellow pulley of the inclined plane and tie it with a small knot. We meticulously thread the opposite end of the string through the additional pulley, where I have expertly crafted a small loop to facilitate the smooth pulling of the string downward. This setup will enable us to adjust and vary the angle of inclination of the inclined plane. We meticulously position the wooden cart, which is enveloped with fabric, onto the inclined plane and attentively monitor the angle of inclination of the plane. At this juncture, by gently pulling the string downward, we progressively augment the angle of inclination until we observe that the cart commences to move. We perform the experiment multiple times, gradually increasing the angle of inclination, and verify at which precise angle the cart will no longer remain in equilibrium. After collecting the data, we will be able to calculate the coefficient of static friction between the cart and the inclined plane. This is because in the condition of static equilibrium, when the cart is stationary on the inclined plane, the relationship holds that the parallel component of the weight force is equal in magnitude to the static friction force, but the two forces will have opposite directions. From this particular equation, we can subsequently derive the coefficient of friction that exists between the cart and the inclined plane. This coefficient will be equivalent to the tangent of the angle of inclination of the inclined plane, with the base of the sine bus. Let us proceed to repeat the experiment utilizing stackable masses. By doing so, we will effectively increase the overall mass of the cart. Now, let's carefully stack the 50-gram mass and gradually adjust the inclined plane until we achieve the angle at which the equilibrium condition for the cart ceases to be valid. As a result, we proceed to ascertain the static friction coefficient once more. By performing the measurements repeatedly, we will be able to observe that the static friction coefficient remains unchanged, as it is independent of the overall mass or the contact area between the cart and the inclined plane, but solely relies on the materials of the surfaces in contact. We will carefully observe how the angle of detachment that is obtained remains consistent, both in the scenario where we have solely the cart and in the situation where we have added additional mass to the cart. Professors, thank you very much. See you at the upcoming experiment.